So my story is that I've been working mainly in classical machine learning since like 1990, that's when I started in Nijmegen. So I've seen the whole development of the AI field and also contributed a little bit to that. When it got big, like 2008, I essentially left the field a little bit because I felt that the conferences were too big and it was no longer conferences of scientists, but a lot of consumers there, people who come to a conference to get something, not to contribute. So I moved another circle, I moved more smaller places. I was doing from 2005, I've started doing control theory. I'm going to talk about that stuff now also. I worked on that from 2005 to about 2015, mainly with a focus on robotics. And then I was looking for something else again, and I have a background in theoretical physics, and I thought, quantum would be nice to see connected with machine learning to see what it can do for me and for, the sort of the thread of my research that's been main theme has always been efficiency of computation using methods of statistical physics, and so maybe quantum can also help in that respect. So that's how I jumped into the quantum thing. And then recently I thought, well, hey, this control theory, maybe that's good to connect actually with the quantum stuff. So this is what is going to be the topic of today.
So just before you start, I didn't make the screen big.
It's the same.
Oh, there we go.
Essentially the same.
It's equally big, right? It's big enough. Okay. So this is the quantum picture, right? We have a Schrödinger cat that can quantum state can represent multiple outcomes. Now you may be familiar with probabilities, then you could toss a coin, and it can be head or tail, and it's head or tail. It's one of the two, but you don't know which one, and there is an uncertainty about which one, and this uncertainty is modeled by the probability distribution. It's either head or tail. In the quantum case, you have this cat is dead and alive. So that is sort of the mind twist that this is in reality, there is a superposition of realities. This is happening at the same time. And of course, if you want to represent multiple objects, things at the same time, then quantum is great because you can use that kind of superposition. So if you have one bit, you can represent two things. If you have two bits, you can represent four things. And so this goes exponentially up. So that's the hope that with a quantum computer, you can represent many things in parallel and get then in principle a very large speed up over your sequential computation that you have to do classically. Okay, so but of course the world is not as easy as that. And so there is some theory. Which is not my field, but this is, so people talk about quantum advantage, right? So quantum advantage is that you show that on a quantum computer, you can do something fundamentally faster than you can do on a classical machine. If you cannot show that, then there is no point in using a quantum computer and the field is dead, right? So you have to show that it's critically depending on that. So there is a space of problems. So you may be familiar with the problems P. These are polynomial time solvable problems, like sorting cards or sorting algorithms or something like that. So these are easy algorithms. So as you make the problem larger, you only get a polynomial growth of the computation time, and that's fine. And then there are these NP problems, which are thought to be hard in the sense that the problem complexity scales exponential with the problem size. So if you want to solve a traveling salesman problem on n cities, then the time that you need scales exponentially with the number of cities. Now there is this technical class, we're not going in detail, about bounded quantum polynomial, which is thought to be problem. These are things that are solvable in polynomial time on a quantum computer. And they are thought to extend beyond the class of problems that can be solved polynomially on a classical computer. And there are two very well known examples. One is integer factorization, which is actually the main driver of this whole field, because if it's thought of it, so on classical computers it scales as e to the n to the power 1/3, so it's exponential basically. So on a I have this thing, and on a quantum computer it goes as n squared. Now, if this can be realized on a quantum computer, this is the algorithm that underlies all the crypto that is currently used by banks. So if you, and the crypto safety is relying on the fact that this problem is hard and that you cannot solve it on a classical computer. So if you have a quantum computer that can solve this in n squared time, then all the crypto is dead, the classical crypto. And so this is why banks get interested, and this is why there's a lot of money in this field, and there's a lot of vested interest, of course. Yeah.
If I understand correctly, there's no proof that integer factorization cannot be.
Correct. Yeah. So it's not even sure that this is a hard problem. Yeah, but there's just no fast algorithm to do it, and it's this is the situation. So factorization is highlighted there on the top right. You see, okay, if I want to have the prime factorization of 15, I get 3 times 5. You know, everybody knows how to do that. If I get 91, I get 7 times 13. Or if we give you that big number over there, you have to get the prime factors. Then this is really okay. So this is one of the things that, but of course we have no quantum computer that can do this yet. And that is because the quantum computers that you need to do this problem need to be what is called fault tolerant. And these that means that they make no errors in their computation. They can do the unitary computation that's done by a quantum computer exactly without errors. And that means that you need very big quantum computers to do the error correction essentially. And so in the okay, so this is the roadmap. I hope you can see it. Is of IBM on the quantum computing roadmap. So you see here that here's number of qubits. 2025 is 156, 5,000 gates, going up to 15,000 gates, and then going to 2033, you go up to about 2,000 qubits and 1 billion gates. So this is published. This is on the website. So there's a serious expectation that this will grow, and it's not only IBM. There's also other providers that of course have these kind of roadmaps. And you need to be in this kind of area with thousands of qubits before you can do these error-corrected algorithms. And the question is, can we do in the meantime? Can we do something else? And that is the so-called NISQ computing. NISQ stands for Noisy Intermediate Scale Quantum Technology. And so we have these devices of 20 to 50 to 100 maybe qubits. Can we do something useful with them? So there's a whole industry of people trying to do something. And also the question of quantum advantage is already playing here. Can you do something on that you cannot do classically? So the typical application of the NISQ device is quantum state preparation. And the quantum state preparation is that the circuit does a computation, you feed it with an initial state, you do a computation, you get a final state, and the final state represents the solution to some hard problem that you want to solve. So for instance, the ground state of a complex molecule. So you can use that. So people now do that with certain physics methods, approximate methods, and they have their limitations. If you could do this with a quantum computer, you can get this ground state representation. And from the ground state, you can then do measurements on that ground state, and that ground state will give statistics that will tell you about spin-spin correlation, all kind of things that you need to understand the material property. So this is one type of application. So drug design, so there's a lot of pharma money and also material design in there. Optimization problems I already mentioned. So this is like traveling salesman problem that I have on the bottom right there. You can have any kind of optimization problem that so you have an initial state, which is easy to prepare on the quantum machine. You run the quantum circuit, and the end state is the solution, represents the solution of this traveling salesman problem. Or in general, sampling from some complex distribution. So you have initial state, you prepare an end state, which represents some probability distribution, and you can sample from that. So sampling is actually the quantum measurement. So if you have a quantum state, for those who are a little bit rusty on their quantum mechanics, so you have a quantum state, and you that quantum state has, you can think of it as a vector. So you have a vector, you have S is a vector of bits, say Si is plus or minus 1 or 0, 1. And then you have a wave function, psi of S1 to Sn. This is a wave function. And from this, you can generate. So if you now do a measurement on the quantum state, you will get the outcome. If you measure all the bits, you get the outcome S with the probability, which is given by this thing squared. So this is a complex number. And so this gives the probability. And indeed, the sum over S of P of S is the sum over S of this thing squared. So these wave functions are normalized, the square normalized. And so this is, so if you get this state represented, if you do a measurement on it, you get with this probability, you get that value, right? And in this way, you can do multiple, but once you do the measurement, the state is broken. So it gets collapsed onto, it's no longer the same thing. It gets affected by the measurement. So you have to run this quantum circuit again, prepare the state again, do a measurement again, do that 10,000 times very, very fast, and then get your statistics. But it allows you to do independent measurement on this waveform, on this probability. And for those who know about sampling from some hard distribution is, if it's not a Gaussian or uniform, is tends to be very, very hard. So this is also a great application. Anyway, so okay, so these are some problems. Now the way that this is done is typically done on a quantum circuit, and so what you do is the following. So you prepare your quantum state, which is this psi, which is a unitary transformation on an initial state. So we start with an initial state. We have the quantum circuit, which is represented by this U, and it's just quantum dynamics is linear. So you just get a linear matrix, basically multiplying this vector, and you get another vector. Okay, and that's here. Now this vector depends on your circuit, and the circuit is parameterized by parameters, which are these theta. Okay, so you get some state. And now your objective is to minimize this quantity. Now you make sure that this thing is normalized always. So this thing is just a norm. So this is 1. So just focus on the numerator. You want to find the theta, the circuit parameters, such that this thing is minimized. So H may represent, for instance, the physics of some large chemical molecule, and you want to have the ground state of that molecule, and then do this kind of thing to read off the properties from that thing. Okay. Now, the length of this vector is of course very big. So if S is plus or minus 1, then this vector is of length 2 to the n, right? Because we have 2 to the n possible states, and then so we have a very, very big vector. So we've got 10 bits. We have a factor of length 1,000. We have 100 bits. We cannot even store it in the computer anymore. Okay, so this and this is where the quantum chemistry also has the problems to represent this. So you want to do this for very large systems, but your quantum device will give you this for free, in a sense, right? This is what the quantum mechanics does. It gives you the wave function, also on 100 qubits. You just have to be able to control it in the right way. So now you have this wave function there, sitting there, you do a measurement on it, and the measurement allows you to estimate by repeated measurement. There's a bit of a complex story here, but you can, and essentially you can measure this expectation value for a certain psi. And so you're bypassing the complexity that is that in the classical machine, you would have to compute this because you would have a matrix with two vectors multiplying and they're all of exponentially large size. It's too big to store in the computer, but you can do it on the quantum device. Yeah.
Example of this unitary matrix that creates all the states.
This is basically, this unitary is a product of all kind of unitaries. So here you see that here you have 4 qubits. There is here 3 operations, unitary operations on qubit 1 in parallel with 3 operations on qubit 2, etc. Then there is some mixing that the qubits are mixed in an operation. I don't think it's elucidating to think of it as a matrix.
Yeah, but physically, what does it mean? Just okay, it's linear algebra combination, but okay.
Well, these gates are like, okay, so if you have a quantum Hamiltonian, you for instance, you have an external field that you can do with a laser pulse. You can rotate the qubits around, and these are these operations there, physically speaking. Yeah.
So I get, of course, that given some psi, you can compute the probabilities by taking the norm or doing measurements. But in the sort of sampling from a probability distribution problem, it's not obvious to me that you can get any probability distribution by doing unitary operations on a quantum state. So is it, can you get
you can.
any probability distribution classical?
You can.
Or
yes, you can, because it basically means if there for any pair of states, is there a U that connects them? This is your question, basically, because your probability distribution is 1-to-1. Well, actually, there's many psi's corresponding to one probability distribution because of the phase, etc. But anyway, so the harder question is, can I prepare any state, quantum state? And the answer is yes. But of course, this unitary is, if you take it in its general form, has an exponential number of parameters in it. And so once you make a circuit ansatz that they do, so okay, we're going to first do rotations on the individual, then we do something else, then we do this. This is a circuit ansatz. Then in that circuit ansatz, you may get properties that it's universal in the sense that you can go anywhere, provided that your circuit is deep enough. Okay, you get those kind of trade-offs. And then there's a problem because the deeper your circuit, this circuit depth translates physically into time, and quantum coherence has a finite time, and so you want to have your calculation over within that coherence time, because afterwards you resort to classical and you lose your quantum advantage. So there is all kind of problem there.
I was thinking also in the life of stochastic process where you don't have unitary evolution, where you have sort of Markov-like evolution.
Yeah.
Pure state. But that's not a problem. You get
that's different.
PS can be
what?
Can be I don't know, a steady state of some Markov process.
Well, this is reversible, huh? I mean, so these are unitary. So these are rotations. You can think of them as rotations. And they can be you can rotate back. If you have a classical stochastic process, there's no such thing.
There's no such thing, exactly. But you can still represent those probability distributions in this way.
Of course, but then you have a classical machine, so this is a quantum machine.
Can I also ask a clarifying question? So for these 4 qubits, how large is this data? I mean.
Okay, so the unitary is 2 to the 4 times 2 to the 4, right?
Mm-hmm.
And the number of parameters is basically that 2 to the 4 squared.
Okay.
That's the number of parameters that you get in general. Right?
That's a very.
Doesn't it depend on how deep your circuit is? The number.
No, if you present it like this, it's just a unitary mapping 2 to the 4 to 2 to the 4. So it's the number of parameters is 2 to the 4 squared. But if you make a circuit, you have one parameter for this one parameter for that, and there's parameter sharing over different layers. There's all kind of engineering going on to get this.
Per layer, there's 2 to the 4 to the 4.
Yeah.
And is it the case that only for certain ansatz of these circuits there can be a quantum advantage?
Yeah, that's also the case. Yeah, that's also the case. So there is certain circuits that you can efficiently compute classically, and then there is no quantum advantage. That's also. Anyway, so So here, so we have this quantity, we want to optimize it. So what you do is that you compute the gradient and you minimize this quantity by gradient descent. So that's that you do in a classical machine. You compute a new theta, you load it onto the device, you generate new quantum state, and you iterate, right? So this is what called quantum variational algorithms, and it's the standard way to do these NISQ devices. Now the problem is that these gradients, they tend to vanish everywhere. This is a problem of the quantum computing. It is related to the unitarity of the operation. So what this means that if you initialize your parameters somewhere, so here you see this error as a function of the theta. You initialize error anywhere, the probability with probability 1, your gradients will be 0, or vanishingly small, exponentially vanishingly small, exponential in problem size. So that is a big problem. Yeah.
How can you find these gradients when you run it through a quantum computer?
Sorry?
How can you find these gradients because you compute this expectation?
Yeah, so there's a whole story there. Yeah. So they use finite differencing. So this is a big problem, and it's been sort of a stumbling block in the use of this method, for instance, for quantum chemistry.
But can you explain again why you have this flat lost landscape? Why do you have this flat landscape?
No, I cannot explain that. Intuitively the picture is that if they compute an average of the gradient, and they show that that's 0, and then they compute the variance of the gradient under some distribution, which is called the Haar measure on the Hilbert space, and that variance they show goes as exponentially down in the number of qubits. That's the construction that they have. So this is the picture in the back there. Okay. So that's one story. So now instead of using a digital circuit, as I just showed you, there is also a way to do it analog. And that works in the following, that you say you have a bunch of qubits. So okay, so here, what you do here is that you basically engineer all the interactions in the way that you want it, right? And you make sure that your hardware has then to take care of that it can make these gates. So here you have single qubit gates, but you also have gates here on 4. Well, maybe the better example would be on 2, but then you make a design which has 2 qubit gates, etc. You engineer it in this way. An alternative is that you say, well, I have just a bunch of qubits, and they are connected somehow by their physics. They interact, and maybe I can just use that interaction to my advantage and just steer the individual qubits, control them, right? And so then you get that you start with an initial state, you evolve according to the Schrödinger equation, you get to a final state with a Hamiltonian that has what's called a drift Hamiltonian, which is the native one, that is the coupling between the qubits. You cannot control that. And then you can steer the individual qubits, maybe with a interaction, where this is a Hamiltonian for an individual qubit, and this is a control field for the individual qubits. And you do that continuous in time, and then your picture will look something like this. This is your control solution then. You use as a function of time, they go like this, and this will steer to the end state. So this is an alternative to this digital circuit. And what people...
Just a clarifying question, so this control is also using external fields?
Yeah, lasers, yeah.
Isn't this destroy your superposition? If you're constantly steering your quantum state, then you're never in any kind of...
Okay, so this is jumping a little bit ahead. So this is I'm talking here about open loop control. So I'm talking, typically your control depends on the state. And if I measure the state, then indeed I have to do a collapse, and then things get hard. So what people typically do is open loop. So you just have a control sequence U, which only depends on time. It doesn't depend on state. There's no feedback control. Okay, and that saves the day. Of course, the challenge is to do the feedback control, which is something I'm not going to talk about today, but which is active research that I'm doing at the moment. Then you do measurements on the system. And if you do a big measurement, it changes the state a lot. You don't want that. So you do something called weak measurement. It changes the state a little bit, but also give you only a little bit of information. And then with that limited information, you have to do then control. But it's a very complex story. So I will not go into that. I will just stick with the open loop control. Now, in these analog circuits, there's a recent paper that if you look for the ground state of these kind of molecules, which are just on 2 qubits, I mean, these examples that are currently in the literature, they're pathetically small. But you get the speed up, the depth of the time of the circuit goes from like 500 to 800 nanoseconds. This is superconducting qubits to about 9 nanoseconds. So it's very, very much fast. It's a very significant speed up that you can get because of continuous time and you're using this drift Hamiltonian. You have much better use of the resources. And here's a little bit larger. And if you compare these times with the T1, which are basically the coherence time on the IBM machines, they're about 70 microseconds. So it's getting in the same ballpark. So it's very significant, this kind of thing.
So by this you mean computing the ground state for these things?
Yeah.
Okay.
Yeah, the depth of the time that you need for the circuit.
Sure. But how big could we scale these?
Sorry?
Or how big molecules could you make these saving?
Well, they did it in this paper in 2021 for 4 qubits.
It's anything that has 4 qubits, I guess, in that paper. But I think Fernando is asking, if you increase the complexity of the molecule.
Yeah, so then you have a hard time running this digital circuit, then you have a hard time running this analog circuit, and that's where the research artery is to push that up to tens of qubits at the moment. Yeah.
So why are they comparing with these coherence times of these computers? Because they're not run on these computers, right? Or are they doing this inside an existing one?
No, they're not doing this. They're doing this in simulation.
Okay.
Yeah, but it's relevant because this is the simulation times that you get, right? This is the time that you would expect to get.
So you still use the digital infrastructure, and on top of that you run like an analog simulation.
You do an analog simulation on a classical digital computer to see how your analog quantum computer would behave.
But say you could do this on quantum hardware.
Then you would expect these times. Yeah.
And you would do it on like this IBM computer.
For instance, yeah.
I thought you're saying that you create something that's not a digital computer, quantum computer. You create like an analog one.
Yeah, but I mean, these computers, these IBM machines are in fact analog in the sense they're analog, but they're used typically in circuit modes where they have discrete gates, etc. But you could use the same hardware for analog computing, and the hardware has a coherence time which is in the order of this.
Right, and this H0 is a property of the quantum hardware.
H0,
The zero Hamiltonian.
This is a property of the quantum. Yeah. So this depends on the device. So if you have if you have superconducting qubits, you have some H0. If you have neutral atoms, you have some other thing. I mean, it's a completely different kind of hardware. It's very hardware dependent. This is for transmon, superconducting qubits. Okay, so we're all together still. Good. So okay, so you could do this also on there's instead of superconducting qubits, you can also have these so-called neutral atoms. These are much slower. They have times instead of nanoseconds, you're talking about milliseconds actually, very, very slow. But they can be easily scaled up to arrays of hundreds. And so you can do interesting things with that. So this is something that is now there is through Amazon Bracket, Amazon has a service that provides a platform on this computer, and you can just access that and you can run your algorithms on that. I haven't done that, but this is something to do in the future. Okay, so the approach that I want to sell to you is to do quantum state preparation as a stochastic optimal control problem. And so I talked about the quantum dynamics as being unitary, and there is no noise there. But I have a stochastic optimal control method, so I need a stochastic problem, right? So my path to the rule approach only works for stochastic problem. It doesn't work for deterministic problem. So I need a noisy problem. And actually, it's good because there is noise, because the quantum systems are not isolated. They're open. They are always interacting in an environment. And there is a sort of a stochastic description of a quantum dynamics in in the context of an environment. And so this is so-called open quantum systems. And this simulation with the stochastics is known as quantum trajectories. So I will formulate the quantum state preparation on the level of the quantum trajectories, and then formulate it as a stochastic optimal control problem, and then use my path and control methods to solve that. So that's a little bit, that's the approach. So the outline is that I will tell you first about stochastic optimal control in the classical case, and then I will tell you about open quantum systems and the unravelings, and then I will put everything together, and I will give you some first results that we have. Okay, so control. This is there's many control problems, right? There's the dog herding the sheep, and there's a kid stacking blocks, and there's bird flying, and there's finance. So many kind of control applications. In general, the control problem is can be formulated as following. You have a current state. I'm in the current state now. I want to go to some other state in the future. How do I get there in the fastest, cheapest, best way, given some cost function? And so in this case, the cost function consists of two terms. One is how well he succeeds in hitting the guy on the head. So there's a quadratic penalty which scales with the distance from the guy. So if you're off, then you get a big penalty, and if you're on, you get a low cost. And there is a cost in swinging this big tree trunk, right? I mean, there's different ways to do that, and it can all handle the same thing, but there's different energy involved in the muscle, etc. So that's called a path cost. So path, the whole path, the trajectory, and then there's an end cost, and the sum of these two is what needs to be optimized. Okay, so this is the control. So you get a cost, which you have a dynamics, and you specify a control sequence that gives you then the evolution of the dynamics over time, and there's a cost which is an integral over the time interval of that cost, whatever you have, path cost and end cost, and that's what you want to optimize. This is your control point. Okay. So but there's an interesting twist with stochastic optimal control. So you can do this deterministically when there's no noise, and you can do this in a stochastic setting when there is noise. And you might think that, if you add noise, you just get a little bit of noisy version of your control. There's nothing interesting there. And indeed, there are special control problems where that is the case, particular linear problems with quadratic cost. There's nothing interesting happening if you add noise, but if you have nonlinear problems, things get very, very interesting. For instance, here in this case of this spider that wants to go home. So the spider is here facing this future where there's a lake here, there's a rickety bridge over the lake, or he can walk around the lake and go home. These are the two versions that he has. Now, if there's no noise in the problem, the spider will just simply walk over the bridge and go home. That's the end of the story. So that's the optimal control solution in the noiseless case. But in the case that there is noise, so the spider maybe has been drinking a little bit and wants to go home, and as you may also have from your own experience, that if you use alcohol, that if you want to go right, maybe there's a 10% probability that you're actually going up left. And then if that happens on this bridge, you may fall off. And as we all know that spiders, they hate to get wet. So the expected cost of this bridge in the presence of noise becomes very, very high, basically effectively closing this door off. And so then the optimal path is to walk around the lake. Very easy. And what you see is that you basically see a phase transition here. There's a high temperature regime, whereas the noisy case, and there's a low temperature regime, which is the deterministic case, and you get a qualitative change when you change the temperature. You go from water to a vapor, right? And so you get basically a phase transition here. And here's this exactly the same thing happening. Okay, so this is interesting. Okay, so let's so stochastic optimal control. So we have dynamics. Dx is some function which may depend on the state. X is the state, maybe a vector. U is a vector of controls. And then we have some deterministic part, and we have some stochastic part. This dxi is Gaussian noise, and this is known as Ito calculus. You don't have to know the details. If you just have this term, so if G would be 1 and F would be 0, you would get a Brownian motion, just a diffusion process, right? It goes like a diffusion, like smoke, diffuses in air. And so there is a covariance, and the typical thing of this is that's very well used, often used, is that the variance, so the square of the deviation, goes proportional to delta t, right? So the psi itself goes with the square of delta t, and this is very key in the whole Ito calculus, and it's okay. This is very standard kind of theory. Okay, so we have now the dynamics, and now we have a cost, which consists of a path cost, which you integrate over a time interval. Some the status and the control, etc. And then we have an end cost. And then we have to take an expectation value, because if we use different realization of the noise, we get different trajectories x, and we get different values here. And so we cannot optimize a stochastic quantity. We can best, you have to take some moments of statistics, for instance, the mean. We do this, okay? And
quick question, what is this V here? What is that?
so that's a path cost. This was in the, in the brute swinging, it was the cost of exerting the force. So it could be like u squared or something like that, right? And it can also depend on the state where he goes. You may not want to use some configurations. It's your choice. It's your choice. And this end cost also. This is how well you get it hit it on the head, right? That's this one. Okay, so if you have this problem, you want to find the optimal the optimal trajectory of controls. Right, and we may depend on the state also, right? So it's a function. You want to optimize for a function.
Why does the final cost does not depend on you? Is there a reason?
It could, but
it could in general.
It could in general, yeah. It could in general, yeah.
Then it wouldn't be a final cost.
Yeah, would be, yeah. Well, on the final control, it could. Yeah, it could.
Right.
It could.
Okay.
Yeah, I'm not 100% sure actually.
Okay, yeah.
Okay. I'm not 100%.
Just curious.
Anyway, so because because the way to solve this is what is known in some field as dynamic programming. It's in the control theory, it's called the Bellman equation. You can define a quantity J, which is a scalar, which solves your control problem from any particular time and any particular state up to the end time. Okay? You solve it, you find the optimal control, which is this horrible complex function of x and t, and the value, the optimal cost that you have from that state to the end time, you call it J. Now this J satisfies a partial differential equation. And this is the partial differential equation. So you see the V that's happening here, the F that's here, the G that is there, and there is the phi is happening in the end cost. And this is why I'm not sure, because it should not depend on, but maybe it's not a problem. Anyway, so this is the thing that you need to do. This is the PDE you have to solve. Now, if the problem is linear with quadratic cost, you can easily solve this Bellman equation. But in general, this is a horrible equation to solve, particularly because of this minimization. So it makes it very, very hard to solve. Okay, so here's an example. So for instance, suppose that this is my dynamics. I have a one-dimensional state, x, it's here. And I have time here. And I have my control, and I have noise. And basically, if control is 0, I just get from here, I get a diffusion. I go into the diffusion to the future. And my cost is now that I penalize the control quadratically. And I say I want to be at an end state, which is given by these 2 points. I want to be either there or there, in one of these 2 locations. This is my problem, okay? Now, if I solve the Bellman equation, it's a scalar value for every x and t, and here it is. So red is high, J, the yellow is lower, and blue is lowest. And so you see, and basically the control is given by the gradient of J. I didn't show that, but it's basically what you get here. So basically you go here, you steer towards the middle. And if you're later in time, you have to make a choice, because you have to steer to one of this goal to that goal, right? Depending on where you are. And this gives you the optimal control solution. So the optimal control, so there is something funny. There is a delayed choice, as it says here. So actually early in time, you don't steer to one of the goals. You steer to the middle. You wait. But of course you cannot wait forever, because then you would end up in the middle between the 2 topics, the 2 targets. So at some point you have to decide. When do you have to decide? Well, basically, at any time, you have a noise cone, which is this is the width of the noise. As long as the width of the noise is wide enough to encompass in the remaining time the two targets, then you steer in the middle. But at some point you get closer and you get only on one target, and then you have to make a choice. That's essentially.
In this case, you have to go to either of the two sides.
It's
Like not, you don't have a preference.
no preference, no preference,
Yeah.
no preference.
Just a clarification question. So the colored plot, is that C of U or is it U?
J, that's
It's
J.
J, okay,
It's the cost to go
okay, right. It's the minimum of C, right?
over the remaining
Overall.
cost. So this is the expected remaining cost from here. The respected optimal remaining cost.
Okay.
If you steer here with optimal control from any of these points, then the expected cost under that optimal control is that red color. Yeah.
So what is the optimal path, exactly?
So the optimal path, of course, there is no optimal path. There is just an optimal control function, which depends on state and on time. And so if you are here in the middle, then the noise at some point will decide whether it takes you here or it takes you there. If you are at this intermediate time, you're somewhere there, it will surely steer you here. Right? So this function, yeah, this is basically, you can think of the control is just a gradient of this field, of this thing, yeah.
But is there a risk of ending up in sort of a locally optimal control that's not globally optimal?
Yeah,
Only follow the gradient locally.
well, if you solve it, of course, in this case, I solved it exhaustively, by just discretization, and then there is no problem like that. But if you, for instance, think of your control being parameterized, and you optimize these parameters, then you can imagine that depending on the initialization of your parameters, you may have multiple solutions that you end up, and that it will.
So then finding the local gradient is not guaranteed to get you the best.
Exactly, yeah,
Right.
exactly, yeah.
And that's the only way to get U from J is by local gradient.
If you have J exactly, if you have solved for J without not having any problem with local minima, then your gradient is fine.
Right.
Then you're good. But if you use some parameterized form to find J, you say, okay, J is too big because if I'm living in a 100-dimensional space, I cannot just discretize. I have to make some parameterization, some neural network or something like that. If I optimize that, then of course I'm full of local minimum.
I assume this is an example, but generally, how do you guess the form of this second term? Like you have now your harmonic form like u2 squared, is divided by 2. So this is what determines your cost function, the form you guess there, or
It's user defined.
huh?
It's user defined. So
it's but like the example you gave.
you can choose it the way you want.
Okay.
That's also coming back to J's question, but X of T depends on U, right? Or
X of T depends on the past use. Right,
it's
so-
also on the control U.
Huh?
On the control U also, right? Because that induces the path.
So at each time, at any time you do this. So you are in a current state X, and your change in X depends on your current U.
Yeah, but then the phi X of T in the phi X of T depends on U, right? Implicitly.
This one depends on the whole path, on the whole sequence of controls.
Yeah.
So this depends. This X of T, of course, is the integral of all the control, right?
Yeah, but it's phi of XT is the same in the case where your random path got you there versus where there you had to control it.
Yeah, there's multiple ways of getting there.
So in that sense, it's independent. It doesn't matter what you did to get. Yeah, it doesn't matter, but when you're optimizing over U, X of T will be a function of U, right?
Well, but it's a stochastic, right? So there's a stochastic component. So you can get from 0 to 1 in this interval by choosing U as 0 and just choosing all kind of noises, or choosing the noise 0, which could also, with probability 0 happen. and having a certain use. I mean, there's multiple ways to get there. Yeah.
It's how large is the space where you're looking for use? It's only deterministic functions, or
Sorry.
you're looking for deterministic controls.
Yeah.
Not looking for Markov chains.
Yeah. Correct. Yeah. That is, and I think I believe that is optimal. There's no point in having a stochastic control
For this situation.
Yeah, but you can probably think of situations where it does make sense, but yeah.
If you want to solve, if you have a parameterizer, and you want to solve it kind of globally, your gradients, I guess you're doing a numerical simulation. Are you doing some sort of reinforcement learning in this case?
I'll come to that if I get time. If I get to that. Okay. Yeah. So okay. So this is okay. So you can do this, but you can only do this for small problems, right? So this is, I mean, we have to discretize the space, and it's clear that you have Cursor dimensionality because you have this J, which depends on X and T, and you have to basically discretize over all X and all T, and it just gets horrible. Of course. Okay. So there is this. If you have not linear quadratic problems, then basically you're stuck. So either you forget about noise, or then you can go headway, or you have linear quadratic. But in the other cases, you have basically no way to go forward, except for the so-called path and goal control problems. And so in this case, we have a special class of dynamics, and we have a special cost function. And the main feature is that the control and the noise, they multiply the same nonlinear function of X and T. So before we had F plus G U was this one. This was our DT part, our deterministic part. And we had G times this thing. And now we have it. So we can have an arbitrary dynamical system, but the control acts on it in a linear way. Let's say, right? Okay, this is one assumption. And the second is that the control cost here, which you take the expectation value, so this is the same as we had here, this expression, has an end cost and has a state cost, but it does not depend. It has a path cost, but it does not depend. It depends on the state, but it then quadratically depends on the control. And this thing is added for technicality because you have to take the expectation value, it's actually 0, but later we will need this in our further go. Okay.
What is R?
R is a matrix, is a positive definite matrix.
That quantifies the cost.
It quantifies the cost, yeah. And nu is here sorry, there's a square missing. Sorry, this is I should write here the psi. It should be so the psi transposed is nu dt. So this is a matrix.
Maybe I'm just a bit confused by your notation. If you compare with the previous version, then you have F multiplied by dt and G multiplied by the noise term, the psi, in your notation.
Yeah.
And now you put a deterministic term with U multiplied by G, which is
it was just a specific choice of the previous F.
Yeah.
Right? In which the previous F is FTX plus G U.
Yeah.
So we have
why it's written this way.
FTXUT is then is FXT plus UGX.
Yes, exactly.
Yeah, and the U
And the G XUT is just the G.
Yeah.
Yeah.
So, I mean, is this a particular class of differential equations? I mean, does it restrict a lot? I mean, for example, just as an example, does the Langevin equation fall under this?
Well, you can make a Langevin equation of this,
Okay, right.
Yeah. I mean, F doesn't even have to be a gradient flow, huh? I mean, you can have a Okay, so now we're happy. This is then the control class. So we have, and then we can write again the Bellman equation, the same. But now by construction, we have here this quadratic term because of this cost. and we have here this linear term because of this thing, and we can do the minimization. Right? We can do this now. Okay, so we can optimize this. We do this minimization. We find that U is this thing related to the gradient of J, and we can plug it in, and then we get a horrible expression. Okay, we can do that. Okay, and now, but now if in that expression you define a new field which is called psi, which is minus the log of J, so you do change of variables, and you assume that there is a relation between this matrix and that matrix. Basically, the relation is that the product is proportional to the identity matrix, or in other words, R is the inverse of the noise matrix, or variance matrix. If you assume that, then this thing where you filled in this U, you get nonlinear terms, right? You get the gradient J squared because we have U squared, right? This nonlinear equation, all the nonlinearities vanish. So they all fall away, and you end up with a linear partial differential equation, right? This is the same as the Bellman equation that I had before. I have optimized for U, and then I have used this transformation, and I use this identity, and I get this linear equation. Okay, yeah?
But that's somehow saying that my cost is the inverse of the noise.
Yeah. So I'll give you So I'll give you an example. So suppose that I have dx1 is u1 dt plus d noise 1, and dx2 is u2 dt plus d noise 2, right? And suppose I have a control cost. I have R is R1, R2, right? It's diagonal. Yeah. And I suppose my noise is nu1, nu2, right? So I have that. Right. Then I find that I need R times nu is lambda identity. Yeah. So I will find that R1 nu1 is equal to R2 nu2 is equal to lambda identity. Is equal to lambda. Yeah. And so it means that in directions where the noise is large, your R is going to be small. And that means that in your quadratic term, so you get U dagger RU, if R is small, it means that your controls can be large. So in direction of large noise, you have large controls. In the direction of small noise, your R is large and your controls is small. In the extreme that you have deterministic, if your noise is 0, then your R is infinity and your control is 0. So you can only control directions that you also have noise. There is a certain proportionality between the noise and the control.
But this could be true for situations in which R and V are not there.
Of course, I mean, this is an example. I mean, yeah, I just put this. This could be not that you can make this. These are just for illustration. Right. Or these don't have to be diagonal. Yeah. So okay. So we get this linear Bellman equation, basically, and the end cost now is going to be the exponent because of this relation here. So we now have to solve this backward. Now this backward equation is also known as a Kolmogorov backward equation in statistics. And there is an equivalent forward equation, which is known as the Fokker-Planck equation, which is the corresponding forward equation. This one, which you would solve with initial conditions. So this one you solve at the end time, condition at the end time. This one you solve with initial condition. And there's a third description, which is as a stochastic process. And the stochastic process you can read off from the Fokker-Planck equation. So this is the drift term. This is the diffusion term. So we know that. So we get dx is f dt plus g dw, which is that we had. Look at this f dt plus gw. So it's the same that we get with control 0, right? This, and then there's this funny term. And this funny term kills probability with a certain rate. And the rate, so x, the particle is killed with probability V over lambda dt in each time increment, and it's at the end time it's scaled with probability psi over lambda. Right? So this is a probability. This describes this trio of equations describes a stochastic system which is not where the probability is not conserved. So probability is scaled over time. So the integral of the probability distribution, the marginal probability distribution integrated over space is not constant, right? Okay, so that's this. So this is okay. So yeah.
Normally, I always go from the differential equation to the Fokker-Planck equation. So I have this f and g, and then I would only expect that the Fokker-Planck equation also only depends on f and g. But now there's suddenly this v overlap that.
Yeah, because this stochastic process is running in parallel with this killing process. So you start with 100 particles, and then you do a step, and then you toss a coin and you kill particles with this rate. Now you have to think about normal, about you can kill, or you can also create new ones. You have to, you can create extra particles, and there's a normalizer. There's these kind of things for implementation. But this is sort of the picture that you have. So indeed, F corresponds to this term in the Fokker-Planck, G corresponds to this term in the Fokker-Planck, and this term corresponds to the probability killing.
But if you have a normal physical process which preserves probability, that's term 0, right?
Yeah, but here this term comes out because we're not solving any kind of process, we're solving an optimal control problem here.
Okay.
And this is saying that this dynamics is actually solving your optimal control problem. Right? Yeah, it's a special. Okay, so now this and I want to point out this relation, but then further mathematically you can see, well, this is a linear partial differential equation, and we know that it has a solution as a path integral. This is just Feynman-Katz's story. And what is the path integral? Well, it's basically you integrate over trajectories. Tau is a trajectory running from 0 to term under this distribution, which is given by the uncontrolled dynamics. This is the dynamics that you get when the control is 0. This is this Q. This is the distribution of trajectories under control 0. And weighted, where each trajectory is weighted by a factor, which is this killing factor and the end cost killing factor. So instead of doing this stochastically at each time, you can also say, you can also weigh the particles, the trajectories, and you get that. Okay. Okay. We're still together? Good. Okay, so we have now a solution. We have the solution of the optimal control problem because psi specifies J, and we take the gradient, and we have the optimal control as a path integral. And this path integral we can sample because we can sample these trajectories, and we weigh all these trajectories by this thing, and we can do that. Okay. So here's the same example again. So we now have the same dynamics, we have the same costs, and now we have the solution, which is, so this problem is of the path integral form, of course, because f is 0, g is 1. And so we have here this optimal control solution for J, and the gradient is given by this. So we can, in principle, we can think about conceptually, we can at each point in xt, we can do this and get the solution everywhere, and then take the gradient and then do it. So the way, for instance, here I've illustrated how the solution looks, how you compute the solution at, for instance, at time 0 and state 0, right? So we sample from the uncontrolled dynamics. What does it mean? We said U is equal to 0. So we get a pure diffusion. So we get these diverging paths. And then we color with this term, which is just the end cost. So depending on where it ends, we give a color to the whole trajectory. And that's this sum, this is a sum of numbers, gives me the optimal cost to go. This is what the theory says. Okay? But this is how this works. Okay. So this is, here's a...
Yeah, just
what is the advantage of using the path integral?
Well, the advantage is that you in high dimensions, that you're sampling instead of that you have to discretize. And so I mean, of course, you don't solve the curse of dimensionality, but it's generally believed that sampling is a one of the better ways to deal with high dimensional problems.
I mean, so the path integral expression has now a slightly different form. It has phi only, and previously it had an.
Yeah, because there's no path, there's no v here.
You don't have it.
V is 0. Yeah. Okay, so here you see a video of some car racing. It's using, so it's actually working on this. So here you see yeah. So this car is fully autonomous, and it has about 10 or 15 degrees of freedom, so 15-dimensional control problem. And it has so you have the steering, you have the gas, and braking, and so this car is driving at maximum speed that it just doesn't fall over, and then it's computing the controls by doing this path integral here. So at each time there is a 10,000 trajectories is sampled, and then from those the optimal control is computed, and that is sent to the wheels, and then time goes on, and that repeats this. And it's fully autonomous. So you see here very nice nonlinear stochastic optimal control solution in real time computed in a high dimensional system. So I don't think there's any other method that can actually do these kind of
So
things.
here the aim was to have maximal speed given the control parameters.
And to stay in the track. No, the speed. I think the speed was sort of given as a user defined. And then the control was basically to manage to stay on the road, because there's dramatic videos where you see actually this where you see this it's like skidding. Yeah.
I guess that's saves on control if you do this nice drifting in the corner. That's good for your cost.
Yeah, it's even there are slow motion videos that you see the two legs, the two wheels.
So how are there 15 degrees of freedom here? What can this car do?
I don't know. I mean, yeah, I don't know. I mean, the degrees of freedom is the state space, huh? And then there's the control space.
Okay.
So they're different dimensions.
Okay.
Yeah. Anyway, so I have. Oh, here you see the slow motion. Anyway, okay, so okay.
Why are you not in this self-driving?
Huh?
He's now reusing self-driving car.
Well, if you don't care about pedestrians and stuff.
I think that this thing would go faster around the Formula 1 track than a human driver.
Yeah.
If I go on this speed, I have an hour more. So this is not so something we have to decide. Can maybe what time shall we set? Because I don't want to abuse your time.
No, just you have 25 minutes.
I have 25 minutes. Okay.
12:30.
Okay. Okay. Well, I think maybe well, we haven't even got to the quantum part. So, okay. So. Okay, so important sampling. Now, so I told you that if you sample with 0 control, you can, in expectation, you're computing the right thing. But there is a massive variance in that expectation, and it's very unreliable. And so that makes the idea for the case for important sampling, and it is very simply explained the following. So we have this psi, we had before this expression as this path integral. And now we sample from Q, which was this control sampling with control 0. Now we replace it by another control. We sample from with using another control, and we multiply and divide, basically, right? And then this term actually turns out it can be absorbed in the exponent, and the whole thing becomes this. And this is this S that I had on the first slide. It's this S. So the effect of so if the controls is 0, you see we have the same term. And if the controls is non-zero, this is the effect of the control thing. Okay, that's what's happening. So we can not only do this with zero control, but we can also do this with non-zero control, and we get this expression. And so then the optimal cost to go is then this, and actually you can also compute the controls, which are the expectation over the noise realization. So these are correlated because there's noise also appearing in this ES. And so there is this formula for the optimal control. So, okay. So if you estimate, so all the controls give you, all the sampling controls give you an expectation the same quantity, but some have a much larger variance than the other ones. And so we can quantify, so we can basically say that the optimal control is, from this formula, is a sampling control plus this thing, and we write this as weights, which are basically these factors, where we have one number for each trajectory. We run n trajectories, and so we get this thing, and we multiply this with the noise, and this is our estimate. Okay, and then we can define the effective sample size, which is I use n samples, but effectively I have much less. For instance, if there is one sample that dominates all the other ones, it gives a weight that is much larger than all the other weights, then effectively in this sum, I'm just summing a lot of zeros and only one. Effectively, I have only one sample. And so that's the idea of effective sample size. And the effective sample size is related to the variance of the weights, of these weights. If the variance is 0, that's optimal. Okay, and if you have imbalance, that's suboptimal. And you can write it in this way. So this basically gives you the effective sample size, the effective number of sample scales between 1 and the total and big N. Now there is a relation between the U that you use for the sampling and the U that you want for the optimal control. These are two different U's in principle, but they go in the same direction. So you can show that better U's, in the sense of smaller control cost, better, are also better samplers in the sense that they have a smaller variance of the weights and they have a higher effective sample size. And the extreme is that the optimal control, the one that minimizes the control cost, is the optimal sampler. And the optimal sampler has 0 variance. Okay, the very weird thing, because a 0 variance means that this thing, this quantity has no variance, right? And that is very strange because if you look at its definition, here it is. So I have noise. There's this dynamics depends everywhere on the noise. So this is a noisy quantity. But if and only if U has a particular functional form as a function of x and t for all x and t, such that it's optimal, miraculously all the noise vanishes in this expression and it becomes a deterministic quantity. And if you sample with the optimal control, you only need one sample. Okay. So, but okay, of course, that's not so practical.
You can solve the optimal control problem by just saying the stochastic integral must be 0, and then saying the integrand must be 0, and that is your optimal control.
Yeah, if you can solve that, that's well, good luck. Yeah. But in principle, you're right. Yes. Yeah, in principle, you're right. Yeah. So here you see that illustrated. Here is the same problem. Here we have a 0 control. We get a very low effective sample size, about 2 out of 10. 10 samples were drawn here. Cost is 31, is very high. Here you use the optimal control. You see that you get 9.5, almost all the samples out of 10. You get a very low control cost. Here I use as a sampling control half the optimal control. Just this optimal control divided by 2. It's suboptimal, and you get something in between. Okay. Now you can also parameterize the control, and now the things get a little bit more nasty. So because of course computing the control for each x and t is not a feasible issue, so we have to parameterize it, and then you can use a theory which is known as a cross entropy method. It's also known as statistics, and you can apply it to these trajectories, and you can obtain an update rule for the optimal control as a fixed point of that cross entropy method, where you say the optimal parameters are then given by the parameters plus this expression. So you see here you have the weighting over the different trajectories. You have here the gradient of u with respect to the parameters. So if it is, for instance, a linear parameterization, this would be an easy term. And you have here the noise realization at each time, and you get the stochastic integral here. So anyway, this is what you get. These are the weights, and this is the tau, are just the time trajectory, and they're sampled from PU, right? This is from this thing. Okay, so when the model class includes the optimal control, right? So the optimal control can be written as a particular instance of the model class. And if you take the n number of samples to infinity, this estimates optimal control. But of course, if you have finite samples, you get biases. So for the finite n, what you can do is that you do this, you get a certain control, which is supposed to be optimal, it's not, and you just repeat. So you put this one in on the right-hand side, and you compute another one. So you go from theta 0 to theta 1 to theta 2, etc. So you optimize this way. And this is called iterative importance sampling. And here, just for in the case that you have piecewise constant controls, so that the control is only time dependent, so very simple case, but we're going to use that in quantum case, in which you have just a piecewise constant in certain intervals of time with parameter theta, then you get just that this is stochastic integral in this interval. These are weighted by the cost, which the cost depends on the end cost also. So this is then the formula for this iterative importance sampling. Okay, now we go for the quantum stuff. Okay, I just want to remind you that we have the Schrödinger equation in this way, and that we can write a density matrix. Density matrix is the outer product of the wave function with itself. So it's a rank 1 matrix. You can think of it as a rank 1 matrix. And if you fill this in here, you get this equation for the Schrödinger equation. It's just the same equation, but then expressed in terms of rho. Okay? And rho is called a pure state. Right? This is unitary evolution, where basically you can think of this as a rotation in the Hilbert space. So the Hilbert space is a complex vector space where all the vectors are norm 1, and so you have a vector of norm 1, and basically the unitary is just changing it on the back, doing then a rotation. Okay, so that's the density matrix. Now, if we have two systems, 1 and 2, and they can both be in two, it can have two properties, say black and white. So this white and black, this thing, and this can also be white and black. Then the total quantum state can, for instance, be in this state. That is a superposition state. So we have can be both white or they can be both black. Right? This is a superposition, and we can have such a state. And then this is a pure state, right? And then we can make a density matrix of that. So this is again the same as before. So total system is in a pure state. But we can also say, okay, now we suppose we have we look only at system 1, right? And then the density matrix that describes system 1 is sort of the average of the density matrix of this density matrix of the total system. And if you do this average by tracing out system 2, you get that this density matrix is a sum of two rank 1 matrices. So it's not a pure state. Okay? So here, this is called a mixed state. So this is different. So here you have a density matrix with mixed state. So pure state can always be written as the outer product of one vector, and the mixed state has multiple components in there. Okay. So here again, so if you have two states, psi1 and psi2, I can take a superposition, and that's a pure state. Or I can take two states, and I can make two density matrices, and I can add those, and I get a mixed state. Okay. So this brings us to the Lindblad equation. So the Lindblad equation describes open quantum systems in the simplest form as a Markovian process. Think of it as you have a dynamics of a system and you have dynamics of an environment, and you're tracing out the environment. Now, if you know a little bit about stochastic processes, that if you have a Markov system over the total system, and you trace out half of it, the remaining half is not going to be Markovian, right? There's going to be all by couplings over time. It's going to be very, very, very nasty. Here, there is some assumptions made that the coupling is weak, and that the environment is very big, so that whatever the system does to the environment is not affecting the environment, because the environment is very, very big. And in those cases, you can get a Markovian description of the subsystem. Okay, let's leave it at that. And it's given by the Lindblad equation. And Lindblad equation has a unitary part, which I just described before, and it has something else, and which is a coupling to the environment. So here runs sum over repeated indices. This is a positive covariance matrix. This is any matrix, positive. These are operators acting on the Hilbert space. So they could be, so for a single qubit, they could be measurements, so like sigma z, or they could be dissipation, like a sigma plus and sigma s, so certain Pauli matrices acting here. So in the case of a single qubit, this density matrix is a 2x2 matrix, and these operators are also 2x2 Pauli matrices acting on that. Okay, so and this is then okay. This is what it is, coupling to the environment. Now the open quantum system can be described in terms of unraveling. So you can make a stochastic differential equation in terms of the wave function, such that on expectation it reproduces the Lindblad equation. Okay, and the way that you do that is basically the way that I tell this is that you say, okay, I have this, I write it. This is my Schrödinger part, my unitary part. And now I just look at this red part, which I couple my operation ck. It multiplies psi, and there is a noise term. Okay, this is not, instead of dt, there's d psi. There's a noise term here. Okay, this is my proposal. If I do this, if I do this and I want to make this dynamic such that it conserves the norm of psi, so psi stays unit length throughout the dynamics, then I have to add all this other stuff. That's basically what I get there. In the limit of small delta t, using Ito calculus, blah, blah, blah. Okay, so this is, then I have to add that. And where in particular so these C are just these C operators that I already introduced here, but the small c's are basically the expectation value of the Hermitian part of these C's. Okay, and they make this dynamics nonlinear. Okay, because this C is a proportion of psi squared, so it's no longer a linear equation. If these C's are anti-Hermitian, then this term is zero, and the equation is linear. Now, if you compute, if you define rho, so if you define P, if you define P as psi dagger, right? And then you can write an equation for dp is something, right? Because you know deep psi. You have to do the Ito calculus, you put it in, you get an equation for dp. If you now define rho is the expectation value of this thing, you will find that this rho satisfies the Lindblad equation. Okay, so it's like we have like stochastic systems classically, we have a diffusion process that on average satisfies the Fokker-Planck equation. Here you get a unraveling, which on average satisfies the Lindblad equation. And here
what's an unraveling just for, I mean, is there as a technical term somehow?
Well, it's also known as a quantum trajectory. It is called unraveling because I think maybe it's part of the answer is that it's not unique. So this is one way to unravel the Lindblad equation, but there is multiple ways. So one should be stay a little bit away from physical interpretation of this thing because they are these unravelings are not unique.
Can I just ask you another question because I'm not. It seems like it's a thing, but unfortunately I'm not familiar with the stochastic Schrödinger equation. Do you get the noise from tracing? I mean, do you get the noise from the Lindblad equation, or you add the noise?
Yeah, you get the noise from the look here. The mean noise is 0, and the covariance is d, and d was already in the Lindblad equation.
Okay, so you get it from all right.
Yeah.
But now it sort of looks like that you added the noise term in such a way that if you define rho to be the average, you get the Lindblad equation.
Yeah.
That's exactly what you want, or
that's what you want.
Yeah. So So it looks like we're going the wrong way around. But so you design this stochastic equation in such a way that it has on average the Lindblad equation.
Yeah.
Okay.
Yeah, exactly. That's
So
what you do.
There was no other reason for looking at. There was no other heuristics for the stochastic term other than it gives me the Lindblad.
Exactly. And so you can do it with a diffusion process, like a continuous diffusion process, but you can also do it, for instance, with Poisson jumps. So it's completely different. You can also make Poisson jump processes here in such a way that also on average you get a Lindblad equation. Okay, so there is different ways to get a stochastic description. Now, any unraveling is sufficient if you just want to control the Lindblad equation, right? So if you want to do that, so this is the objective that I'm following here. Okay. Okay, so all good? Okay, so here okay, so measuring a single qubit. So here we have an example, 1 qubit, h is 0, so no unitary part. There's only one C operator, which is sigma Z, which is a Hermitian operator, and we take D as 1. Okay. And so then the Lindblad equation is right, this equation, this term is 0, D is 1, there's only one term here, and you can write it as this. It becomes this, okay? It's the matrix equation. Rho is a matrix, sigma Z is a matrix, Pauli matrix. Look at this. The unraveling takes this form, where M is now this small c that we had before, and it's a real number, right? There's this Hermitian operator, and so we get this for the psi operation, and from that we can also get an evolution for MZ itself, like the moment, like the mean magnetization, right? The expected magnetization. So we do a D on this one, and we get this equation here. And that's plotted here. So you see here time, and you see this thing. Now this, if you take the expectation value of MZ, of DMZ, is 0, right? Because the noises mean 0. So you expect the particles not moving on expectation. But you have that the noise is proportional, depends on the state, the amount of noise depends on the state. Particularly if M is plus or minus 1 here, the noise is 0. Here in the middle, the noise is large. So you have, on average, you have mean noise 0, but you can think of M. So here is 0. So here the noise is large, both sides, but here the noise is small. So that means that there is a net drift actually towards these things because of this. Okay? Despite the fact that the expected noise is 0, the drift is 0. And that's what you see here. So it goes to one of these states, M plus minus 1, which from this you can read off that a fixed point of this equation is that if psi is an eigenvector of this operator sigma Z, which is, so here you see measurement happening in a sense, right? There's quantum measurement. It collapses the wave function from this initial state to that state. The probability that you end up here or end up here is already prescribed here. Here it's 50-50, but here it is you know that the probability to collapse is given by the wave function. So here, if the wave function would start here, you would find that indeed, if you do simulation, you will find end up in this state as predicted by the initial state probability. Yeah.
So this time it takes here, is that somehow a realistic decoherence time of a measurement of qubits?
No, because so there is well, I don't know everything. I don't understand everything about it. It is the problem is that these unravelings are not unique. So I will give you another unraveling. If I replace the Pauli matrix by I times the Pauli matrix, it does not affect the Lindblad equation. Lindblad equation stays the same. But the unraveling, because of this thing, it becomes then this thing, this operator becomes now anti-emission, this thing becomes 0, right? And and so your function becomes your evolution, your stochastic Schrödinger equation becomes linear, and this equation becomes basically the boring DMZ is 0. So it would just be a straight line. So the fact In the nonlinear unraveling, you see the collapse of the wave function. In the linear unraveling, you don't see it. So clearly these are two different things. But both of them on expectation reproduce the same Lindblad equation.
Mainly the expectation being 0.
Yes, exactly.
Yeah.
Which is what the Lindblad equation does.
Yeah, yeah, sure.
Yeah. So that's what it is. Yeah.
Does that sounds to me like actually reproducing the Lindblad equation in expectation value is not so
interesting.
Yeah.
It is indeed not so interesting because so the Lindblad equation is only linear because you can think of it, you do a measurement. So if you use the Lindblad equation for measurement, right? So you have a sigma z. So if you do a measurement, you go onto one state and you have to renormalize that. And that renormalization of this one state makes it nonlinear. If you now say, okay, well, I get a certain outcome, but now I'm going to average with the probability that I get that outcome and sum, then this averaging term that you add, the probability, is the same as the normalization of the denominator. They cancel, and the result becomes linear. So the Lindblad equation is a linear dynamic that describes the expected dynamics under different outcomes, but it doesn't describe a single outcome.
I think sometimes it can. Sometimes there's also settings where you're observing these jumps, right? Like quantum jumps, or sometimes you're measuring these jumps, and then they are visible.
Yes.
But that depends on if you are actually doing measurements on the system.
Yes, exactly. So in this, what I said about the measurement, doing this for the control with the feedback control, there is a part which has to do with the actually measuring, and there is a theory which is called hybrid dynamics, in which you have a quantum dynamics, which is the stochastic. It's coupled to a observation dynamic, classical variable. So you get two dynamics, and you can do theory on that. And it seems to me that in that case the unravelings become unique, and so there things get solved. But at this stage here, we don't have any classical observables. We don't have. Okay, in Jules time. Yeah, so this is an example of an invariance that changes the unraveling, keeps the Lindblad equation the same. And we'll use that later. So here we're going to go into the control. Okay, so here we have now the control problem. We have a dynamics, which is a Lindblad equation. Okay. And we have a Hamiltonian, which has a drift Hamiltonian and some control terms. And now we have our control objective, which is a quadratic cost, we say, on U. And we have an end cost, which is minimizing some operator. So for instance, this operator could be, for instance, G could be 1 minus F psi dagger, and then psi T transpose G psi T is then basically 1 minus what is called the fidelity of psi. So basically, then this end cost will basically measure the overlap with a certain end state phi in this way. Okay, this is an example. But of course, it could be something else. In this case, if we can now, so we have operators C here and we have operators H here. And from the path integral, we want to make this into a path integral control problem. So we have the unraveling here. And we have to make these C operators proportional to this H, because remember, in the path integral control, the U and the noise, they always appear in the same term, right? So that means that these noise operators, they have to be sort of related to these control operators. Otherwise, it's not going to work. And so if you can transform these C's into anti-emission operators, which are equal to these control operators, then you can get this control problem in the path integral form, where here you see this appearing of this term. This is the stochastic term, and then the control term. And the control cost is now this. This was a deterministic quantity, but in terms of psi, which is a stochastic quantity, we get an expectation value in this form. Okay. So here you see a simple example on 1 qubit. I have no no drift Hamiltonian, just control Hamiltonian. So I can rotate in the sigma x and in the sigma y with two controls, ux and uy. So this should equate uy. And I have dissipations sigma plus and sigma minus. And this is a case in which I can, so this is then the control part, this is the dissipation part, and I can make this transformation as I just said. And so I can make this into a path-local control problem. And then here you see the solution, here you see the control cost going down. You see the fidelity of the end state, the fidelity of the end state, which should go to 1. You see it here boosting up. This is the mean over trajectories. The red one is the worst case. Here you see the control solution after some time. And here you see the effective sample size. This is the effective sample size was starting with control 0 was very bad, and then it booms up to a certain value, about 20%. It's not 100% because this is open loop control. So the theory would say that the optimal control gives you an effective sample size of 100%, but it will require a feedback controller, of course. And here we only have open loop control. And this is so here you see that the trajectory is a single qubit. So here's the x state, the initial state. This is the y state, the target state you want to reach. And of course, to get from x to y, you would actually need a sigma z rotation. That gets it very easy there. But sigma z is not one of your control primitives. So you have to do it with x and y. And then you have to use the funny thing that these are not commuting to get this funny trajectory going. So like this, while doing this. And of course, there's a dispersion of the trajectories because there is no feedback mechanism.
Just to understand this, what is on the x-axis there? What is P here?
Where?
On the x-axis on the left.
Here. Oh, these are these important sampling steps. Okay. Yeah, these are the iterations, right? This important sampling. So in each iteration, I have 400 trajectories. And then with that, I compute a new control, and I do that a bunch of times, and I get this. So here you see a comparison with an existing method, which shows a lot of local minima in that. So it does very bad on this problem. So here you see the quality of these solutions. There's about 500 solutions computed with different initial states and different initial control parameters. And you get all these very bad solutions. And this line, these are the path-local control solutions that we find. We don't find local minima. So very reproducible results. Here you see some of these control solutions that try to go all over the place. I'm emphasizing the stochastic optimal control, but actually one way to benchmark it to sell this is that it actually also works very well in terms of annealing. So you can use this, and this comes back to the barren plateaus. So instead of starting trying to solve the problem at temperature 0, we boost the temperature, we boost the noise, we solve the system at there, and then we reduce the noise over time. And so this is a particular case of 4 qubits where that's an NMR physics. So there is here an H0, which is this given by the NMR molecule, and then there's a control Hamiltonian, which can steer the sigma x component and the sigma y component of individual qubits, of all qubits. And so here we see how this drift Hamiltonian is actually coupling qubits, but the entanglement. So this is making the entanglement in the system, and the target state is a GHZ state, which is a highly entangled state. So you have to do the control of the single qubits in such a way as to producing a highly entangled state. And so this is a hard task. And here you see what we this is what we get. So the grape solution, that is this is the deterministic optimal control solution that is out there in the literature, produces this kind of infidelity. So this is low is good. And so if you just run the open system, you get this. But if you start annealing, you can get this arrow down and down and down to actually order 10 to minus 10. You can get very, very low quality error. So here you see the annealing schedule over time. So we're doing this important sampling, but we're reducing the temperature. And so then the control solution, at the end of the day, they look well. This is a piecewise constant. So you get these kind of solutions. They look very ugly, actually. They look very ugly, and it is related to the fact that you have all these non-commuting operators acting, and it makes very, yeah.
So it's the nuclear coupling that does the entangling for you.
Yes.
And you do the rest.
But you just control the single bits. And yeah. And actually it's known that this is universal, that certain of these systems, I don't know the detail, but certain of these systems that ensure that if you have a drift Hamiltonian of a certain type, and then you control only the single bits, that is sufficient to reach any state.
That's really nice.
Yeah, it is. Yeah. Okay, so this is that. So we started with some quantum chemistry benchmark. So this is something that we're now comparing with the VQE, but let me just go fast over this. So here, this is a system of 6 qubits. Of course, the VQE, this is the digital circuit optimization, gives no good results in this case, and we find. So this is something called chemical accuracy. That is the accuracy that you need to get to make it useful for practical applications. And so all these methods should reach the chemical accuracy, and here you see we do that. The squares are, this is iteration over different initial conditions of the quantum state, which is detailed, well, you can also optimize over that. It's done here. And here you see, this is the same plot where, so the red lines are produced with the annealing, and we also do it without the annealing. And then you see that we get these green ones. And basically you see here that we need the annealing in order to get these results. And if we don't anneal, we get results which are very similar to the VQE results. So showing that this annealing really works here.
Is that related to finding this global minimum?
Yeah. Okay, so there's one last thing. Okay, so I'm almost done. So now you want to scale this up on the quantum computer, right? And that means that you want to use a quantum computer to find your optimal controls, right? Like VQE does that, right? They had this quantum state preparation, you do some measurements, and you change the parameters, and you do that. So far, we do this all on a classical computer, and of course, this is never going to scale, right? Because we have to represent wave functions which are way too big. So you want to run this also on a quantum device. So this holds, as I said, it holds for VQE. And it does not hold for all the existing optimal control methods for analog quantum computing. So there are a bunch of those there, but they all only work on in simulation. So you need a classical computer for that.
Why is that?
Well, because it's not so obvious how to. I mean, what you do with these these deterministic optimal control methods is basically they run something called the Pontryagin minimum principle, which is coupled ordinary differential equations, which run forward and backwards, and you have to run them into convergence, and it's not so obvious how to do it on a quantum circuit.
You also have other approaches using these trajectories, right? And then maybe you could use these finite differences to compute the gradients, like what you have to do for the VQE anyway.
Yeah, I don't know. I'm not aware. Let me say, I'm not aware of such implementations. Okay, but this method that we call quantum diffusion control can be optimized on the quantum hardware, and it's not totally trivial. What you have to. So if we look at the update equations, like the simplest form was this form. So we have these weights and we have these noises, which is the noise over a certain interval for piecewise constant. And these weights are these terms. And these are some end cost and then some path cost. And in order to do this, to do these updates, you get the end cost you measure, of course, this term you measure. The controls you also know, these thetas, you put them in yourself, but the noise you don't know, right? Because the noise is generated on the quantum device and you don't have no access to it. And it's key that you have these noises in order to do these updates, because this update equation depends on the noises. So what we propose is that you can actually assume that the noise in the device is very low. So now we're going to switch to okay, let's say that there is no noise like everybody else. We just say with a unitary device. But now we're going to generate a noise ourselves. We're going to put in not just a U, but we're going to put a U in plus a noise. And in that case, so we do actually the same as the quantum device would do, which generates noise, but with the difference Since we put the noise, we know the noise. And once we know the noise, it is sufficient to run, so then we can run these trajectories, measure the end cost, we have the noise and we have everything to compute the update of the parameters. And so we can do the adaptive importance sampling now on the quantum device. And it's in principle, it's efficient. So this is work in process. Okay, summary. New control framework for optimal analog quantum systems based on unravelings and path-level control. Unravelings provides quadratic speed up compared to lint plot. I didn't say that, but the density matrix is so if the wave function is something of size 2 to the n, the density matrix is 2 to the n by 2 to the n. So if you do control of open quantum systems, you have a quadratic burden compared to doing it on the unravelings. Unravelings plus annealing provide improved conversion accuracy compared to closed control scalable quantum computers. And that's the end. We're going to talk about future work. That is here some references, and these are my colleagues that work with me on this project. Okay, thank you very much.